So while everyone's filling that out, I will take the opportunity to introduce our speaker today. Today we have with us Radiasoft research scientist, Dr. Boaz Nash. Boaz received his PhD from Stanford University for work studying beam dynamics in electron storage rings. Prior to joining Radiasoft, he worked at the European Synchrotron radiation facility in Grenoble. On the EBS upgrade, he is an expert on synchrotron light sources and X-ray beamlines, and today he will be showing us how to design an undulator using the Radia app in Sirepo. So with that, I'll leave the poll open, and Boaz, take it away.
All right. Can you hear me okay? Okay,
Yes.
So great. I'm Boaz, and thanks to everybody for joining us today. So yeah, I'm going to be telling you about our Radia application on Sirepo and how to use it for undulator design for synchrotron light sources. So I assume I don't know exactly what everybody's background here is, but I guess that I got a lot of people here that are pretty familiar with synchrotron light sources, or experts, or work at them and such. So just as a reminder, there's more than 50 synchrotron light sources around the world. And here's a overhead picture, helicopter picture of 6 of them. So here's 2 U.S. light sources, the ALS and the NSLS2 in Berkeley and Brookhaven in New York, and then BESSY in Germany, the ESRF in France, MAX4 in Sweden, and the Taiwan photon source in Taiwan. So basically they all have this ring structure, and just as a kind of schematic overview to remind you of how synchrotron light sources work, you have an electron gun that creates a bunch of electrons that gets passed into a linac, which then accelerates those electrons into a booster accelerator that further accelerates the electrons, and then they pass into the main storage ring where they're stored. And in that main storage ring, they're in small bunches, and these bunches of electrons then pass through the magnetic magnets and to store them in the ring, and then also to create the synchrotron radiation that passes down the beam lines and then hits the samples where you do experiments using the X-rays. So there's a lot of different software involved in the whole process of creating, designing, and running a synchrotron light source. There's all of the mechanical engineering software. There's also a lot of beam dynamic software, which Sirepo has a number of other codes associated with it for the beam dynamics. Then there's the magnet modeling and design, which we're going to focus on today. There's also X-ray optics software, and then control system software. Okay, but today we're going to talk about what magnets there are and how do you design those for a light source. Okay, so here's a picture of the 4 different main types of magnets that we have in a synchrotron light source. We have a dipole magnet, a quadrupole magnet, a sextupole magnet, and an undulator. The dipole magnets are constant magnetic fields, and these are used to bend the trajectory and to keep the electrons in the storage ring to make out the circular trajectory of the storage ring. The quadrupole magnets are for focusing, sextupoles are for nonlinear effects, and then the undulator magnet is what creates the synchrotron radiation when the high energy electrons wiggle back and forth inside the magnetic fields there. And these are from the old ESRF pictures of these magnets. Okay, so once you have, so an undulator magnet is essentially, undulators and wigglers are essentially oscillating magnetic fields. So if we have a planar, vertically oriented undulator, then you have a magnetic field that oscillates as a cosine. by is the cosine, with lambda u is the period of the undulator, and then it moves for a fixed number of periods, and then it stops. So the k parameter is the undulator parameter, is proportional to the field times the period, and that determines whether you have a wiggler or an undulator, and it essentially sets the maximum angular deviation of the electron as you pass through. So for large k parameters, you're undergoing large trajectories, and if k is very small, then it's small deviations, and there's a kind of basic size to the synchrotron radiation, and if that's smaller than the oscillations, then you're an undulator, and you get an additional kind of coherent property to the radiation. So really what you need to know is the orbit. Once you know the electron orbit, that's what I'm representing here on this slide, is if you know the orbit of the electron, then you can use this formula from the Lienert-Vickert potentials to integrate over that orbit. Beta here is the velocity, and n hat points in the direction of observation. So you do this integral along the trajectory, and then you can compute the synchrotron radiation, the electric field of the synchrotron radiation for a fixed frequency. So the magnetic field is going to determine the electron trajectory, and then from that electron trajectory we can compute what kind of synchrotron radiation we're going to get. Okay, so the other aspect you need to understand about undulators is in addition to creating the nice radiation, they also have potentially adverse effects on the electron beam. And one way of characterizing those effects is through something called a kick map. And this was based originally on a paper by Pascal Lhomme from 1992. And you do this certain integral of the magnetic fields, the Bx, the different components of the magnetic fields, and you construct this over the undulator. So given the magnetic fields, you can compute these integrals, and these tell you the kicks that an electron will receive. So this can include the nonlinear effects of the undulator, and this is a sort of standard way of understanding how bad of a effect, whether you're going to decrease the dynamic aperture or have other bad effects on the electron beam. So this is radia that I'm going to be talking about. This is one of the quantities that we would like to compute out of the magnetic field from the undulator. Okay, so just to summarize what I was just saying, once you know the magnetic field from the undulator, then you can compute a trajectory for the electron. This could be done in the SRW code. And so you could compute that trajectory, which you could export into another code to compute the synchrotron radiation, or you can compute a kick map and export that into a code like Elegant or Accelerator Toolbox that is going to tell you the impact of that electric of the undulator on the beam dynamics. Okay, so the Radia code was written by Pascal Lhomme, Oleg Chubar, and Joël Chavan. Recently, a couple of years ago, the source code became freely available. So here's the GitHub repository for it. It's a C++ code with various different interfaces to it. There's a Mathematica interface, an Igor Pro interface, and more recently, within the last few years, a Python interface has also been developed. And we at Radiasoft have been collaborating with Oleg Chubar at Brookhaven to to continue development of the code and to work on the interfaces to the code. So one nice way of using Radia is through Jupyter notebooks. Radiasoft has developed a 3D visualization widget based on VTK, and that's available on the Radiasoft Jupyter server. I'm not going to focus on Jupyter during this talk, but we've developed a lot of tools for use of Radia. If you go to this repository here, the Radia examples repository of Radiasoft, you'll see we've developed some Jupyter notebooks that are basically translations of the Python standard Radia examples. So this can really help get you started using Radia in Jupyter if that's the way you'd like to use it. Okay. To give you a sense of how Radia works, this equation here, H equals QM, is sort of the basic equation used by Radia. The M is the magnetization, so you divide up the magnets into subregions. Each one has a magnetization associated with it. Then the H is the magnetic field in a position you'd like to calculate it. So Q is a matrix that connects a given subregion to a magnetization to a magnetic field elsewhere. And that's one of the innovations of this method that by the authors of the code was to come up with these explicit formulas for this interaction matrix to compute the interaction between the magnetization and the magnetic field. So given a magnet structure, you have polyhedra, and then you construct your magnet out of polyhedra, and then there's a magnetization in each one, and then using this matrix equation, you can figure out what is the associated magnetic field on another polyhedra. So out of all the polyhedra that you build your magnet, you need to construct this interaction matrix. And once you have that, so that interaction matrix tells you how to go from the magnetization to the magnetic field. I give the reference here. There's a few other references, but okay. So once you know the magnetization, you have a starting point for the magnetizations, and then the material property comes into play. So you need to have an MH curve, a magnetization magnetic field curve. This is an example for vanadium permandur. Once you know the M vector, then given the interaction matrix, you get the H vector, and then you need to iterate that so that you get a consistent, self-consistent distribution of magnetization. So overall, there's 3 parts, and then once you have that same matrix will be able to allow you to calculate. You'll be able then to using the analytic expressions, you could then calculate the fields where you want them. So there's 3 parts. There's the interaction matrix construction, the relaxation, and the field calculations to a given Radia calculation. So the interaction, this has now been parallelized at least. So two of those 3 steps have now been parallelized. So the interaction matrix has been, and the field calculations have been parallelized with MPI, and we've found good scaling properties demonstrated on a range of cluster architectures. The parallel Radia can be accessed directly from Python and is available in Jupyter notebooks, and then the Sirepo application I'm going to be showing you also can take advantage of that. And this plot here just shows the good scaling properties of the interaction matrix construction and the field calculations. And this was work done by Anushka Banerjee on the Brookhaven and NERSC clusters. And so those two steps are parallelized. The relaxation process has not yet been parallelized, but work is towards this goal is underway. And that would be using OpenMP. Okay, so that's the end of my overview here. So now I'm going to switch over to my demo. So if you'll follow along, if you go to sirepo.com, then we'll see how the Sirepo application for Radia works.